Hello, everyone. Thanks for joining the talk today. I am Kevin Wang, currently working on multiple projects on the CNCF. And my personal background is more about scheduling, and actually I started contributing to Kubernetes scheduler in the early days. And during recent years, I have been working on the Volcano project, as well as Karmada project. So today I would like to share my thoughts and my experience working on the multi-cluster AI infrastructure, especially for a lot of Day2 optimization. So a little bit background of the talk. Why we need a multi-cluster? Actually, we all know that there are kind of multiple backgrounds. Some of the company, they have multiple regional business. It results in physically divided distributed clusters, and also some of the users may run into the hardware procurement cycle issue, so they have to kind of extend their workload to the public cloud so they can rapidly get some of the resources. And also, during my experience, I have met a lot of end users. They are kind of restructuring their resource pools as their business grows. So previously, a lot of business teams, they would independently build and manage their own cluster. And later on, they went to the structure that have a shared infra team to provide the all the maintenance and also share the technology. And also, why not a few just hyperscale clusters? A lot of users said it's just very hard to rebuild, and also, maintaining large-scale clusters can be very hard. So that's how the story begins, right? So this is just a very brief architecture of the multi-cluster AI platform. So actually, for the in-cluster scheduling, in-cluster workload management, we know that the Volcano project has done a very good job. It helped provide a lot of functionality to support AI batch workload-friendly scheduling features, as well as queue features and resource sharing among queues, and also priority based on queues and capacity management sort of things. At the multi-cluster, actually we can call it just a federated layer. We can use Karmada to manage the cluster healthy state, and also propagate the workloads to the clusters according to your preference. Whether you would like the workload to be kind of divided, or just scheduled to some of the cluster, or replicated. In the case of managing AI workloads, most of the case we will just find one of the cluster to get it scheduled, especially for training workloads. And during my discussion and collaboration with a lot of end users, we found that actually there are some of the assumptions and the design principles very important, and that's being kind of proven multiple times from multiple users. So two-level system is kind of unavoidable. So with that, the layered architecture need to have specific focus loosely coupled. I mean, the federation layer, the federated control plane layer, more focuses on the inter-cluster coordination thing, while the member clusters, they are more kind of focusing the in-cluster thing, and they can be highly autonomous, right? So for the federated control plane, we are kind of not able to store the full detail of the member cluster status, because otherwise, why not we just have a hyperscale cluster, right? And also, like the federated scheduling, you know, should not replace the in-cluster scheduling. It's more likely just collaborating with the in-cluster scheduling. And also, the scheduling in the multi-cluster layer is quite expensive. You find a place to spin up your workload, send it to that cluster, and the in-cluster scheduler made the decision and it turned out no. And then you kind of evacuate it and retry again. It takes long. And sometimes even not able to get things fixed. So we need to optimize the first time attempt. So with the limited time, I will just cover three major challenges I have been working on. First is about the trade-off of the scheduling. Second is about the failover between clusters for the workloads. And the third part is the queuing at the federated layer. So as I said, that actually we are not able to easily kind of store or cache all the cluster status details. We need to kind of balance between, the footprint, the overhead for the control plane, and also we need to take the efficiency and the throughput and also scheduling latency into consideration. So in Karmada, we basically have two major options. One is the resource model. It's kind of compress this cluster status in the control plane, and another one is the the scheduler estimator. So the resource model, actually, we kind of use grades to quantify the cluster, basically node status into some of the groups. As you can see on the right there, it's an example, and also this is actually better, for the CPU or memory intensive workloads like big data, and also it has more better throughput because the scheduling latency is better. All the things you need is inside a scheduler. But actually the accuracy versus efficiency trade-off varies depending on a lot of different effects. So for the estimator, it's actually estimator is quite similar as the in-cluster scheduler. It just not make the final decision, but it will still go through all the scheduling algorithms that you enabled in your cluster. So it will need to watch the member cluster to collect all the basically node and the pod status in memory. And when the Karmada scheduler doing scheduling, we will trigger RPC call to each of the estimator and calculate the max available replicas. As you can see, this would take longer time when doing the scheduling decision. And also, it's kind of still storing the whole cluster status in the control plane. So actually the footprint can be a little bit more expensive. However, actually, when you are doing on the AI workloads, especially for both training and also inference, we think that it's a worthy trade-off because we don't really want waste any of the GPU resources, and also like today, more and more distributed training, distributed inference requirement coming out. We need more awareness of the in-cluster network topology. That's why we need the estimator way for the multi-cluster scheduling for AI workloads. Yeah. So the second part is about the cluster failover for workloads. Actually, during the production resource pool management, we found that it's actually quite complicated, to really determine if there's any cluster failure, and in most of the time, the failure are just partial cluster issues, not critical failures. So people really don't want to kind of drain the cluster or evict most of the workloads, right? And also, we need to distinguish the disconnection and the actual failure status. And typically, we also think that multi-cluster high availability consideration may result in more redundant resources. We need to think about how we really want to deal with the cluster failover. If you don't have enough resource, the failover may, amplify the failure from one cluster to another. That would be kind of unacceptable. So that's why we were thinking how we can, revise the cluster failover mechanism from tent-based eviction to a more flexible way to do it. So that's our kind of revised one. So we think that the cluster status may have multiple resources. We can just, check the cluster list. That's a quite an easy way to check if the cluster is online. And we still need to kind of to have an extensible way to let people implement some, well-known cluster issues and make them to become conditions on the cluster. And also, if you have like infrastructure provider, you may want to have some of the out-of-tree mechanism to call some API to help really found the problem. And for the tent, before we already have like the no schedule tent and the no execute tent at the federated layer, but the thing is that actually the new no execute tent is quite dangerous, because once you add any no execute tent without a predefined toleration on your workloads, it can cause all of them being evicted. So that's why we are thinking, can we add a little bit more, a type of tent that is in the middle, that we don't want really evict most of the applications, but just a few of them. So with that, we actually added the preferred no execute. The interesting thing is that this tent don't actually cause any of the eviction, because you can, it doesn't require any toleration to let the workload stay on the cluster. So then how we can, trigger the some of the workload that don't want to stay when the partial cluster issues appeared. So we are using the failed in the propagation policy to define that. With that, when the preferred no execute tent appeared on the cluster, the eviction manager will trigger the eviction process. And for the both no execute and preferred no execute tent triggered eviction, we will basically include the resource binding to the eviction queue. And we know that it's very important, to make sure the eviction of the workload may result in a workload running in another healthy place. So in the new design of the eviction queue, we are thinking that we can actually import the algorithms of the Karmada scheduler to do a pre-scheduling to check if it's possible to get the workload running. Otherwise, we will just give up the eviction. And also, in the Karmada eviction management process, we already have the graceful eviction mechanism, so we just reuse that. So as I said, that's the most part of the improvement. For as I said, the cluster status detection, we will change from checking the whole clusters instead of to the cluster leads to reduce the pressure to the API server. And also we will add the cluster problem detector to simplify the customization of cluster status collection. And also we are currently working on designing an explicit API for customizing the policy, how you want to tend your cluster by a certain set of conditions. And also you can choose the type of taint you want to add. So that gives more flexibility for you to kind of really manage the eviction behavior of your whole system. Yeah, and in a longer future, we would also take the workload priority into consideration. So make sure, even though you don't have enough resource in the rest healthy clusters, you can still try migrate the most high priority workload to the healthy clusters. So I just provided a link in the slides. You can check out later on. Yeah, so this is actually the new API for defining the eviction behavior, migration behavior that reflects the preferred node execute taint. Yeah, so third challenge I would like to discuss is about queuing workloads. And actually, we have met a lot of adopters. They are trying to use a multi-cluster platform to manage their workloads, like training, and also like computing jobs, as well as this year, more and more inference workloads are making plan to move to this architecture. But as we all know that kind of the scheduler framework have a lot of issues, right? So here are some of them. Basically, smaller jobs always get implicitly higher priority because they are always easier to get scheduled. And the second thing is that the more jobs you created, because the queue inside the scheduler, that would result in more resource you consume. And when there's more and more different type of resources, things get even more complicated. In the talk just before the last one, actually the speakers already give an introduction about the priority-based scheduling inside Karmada. That really helps a lot, but still not enough. When you are providing your platform to multiple business teams, and you would run into limited priority class. And for those workloads at the same priority class, they still met the issues of the fairness thing. Also, another big issue is that we tend to consider serving has higher priority than the training workloads, but we don't really want to preempt them because that would result in waste of GPU from time-wise, right? And also, currently, Karmada scheduler already taking a lot of resource perspective conditions into consideration when it's doing scheduling. But as we know that in the cluster, we are also trying like queue management and also resource sharing between queues, how we can enable it in a federated layer and make the two-level basically decision-making aligned with each other. So that's the things we want to improve. And as we can see that actually Volcano already implemented the queue concept and also like the Volcano job inside the cluster. And with the Karmada design, it's actually quite easy to enable it in the federated control plane because Karmada don't require new APIs. You can just create any CRDs. So the little bit different thing is that actually when you create Volcano job, you also need to enable the Volcano global to make sure it will be mapped into a queue at the federated layer. And also, actually, when Volcano global dealing with the order of the scheduling the different workloads, we just in-queue the resource binding. And also, this is actually relying on the scheduling suspension feature just released in the Karmada latest version to make sure we get higher priority jobs being scheduled by Karmada. And also in the graph, you can see there's an example that we can implement fair sharing between queues. So one of the little bit different thing considering with the Volcano inside single cluster is that today we don't schedule only part of the job. That's a kind of restriction when we are implementing the federated scheduling. So you are not able to achieve fair sharing among job level between different workload. So this is an overview of the Volcano Global. And the first version we implemented just a very basic fair sharing. And in the future, we plan to introduce more algorithms. And also, we are thinking about maybe we can implement like a hierarchical queue and also a lot of advanced queue management features. And also set up alignment with the capacity, resource sharing between the in-cluster Volcano and the federated layer cluster Volcano. So that's all about my sharing. So just a very, I think still the whole work is very initial. And if you have any feedback and questions, welcome to join the community and also help us prioritize our work. Thanks. So any questions? Welcome. All right, if no questions, let's save the time for beers. Thank you. Oh, yes, please. Microphone, yes.
I have one question. Have you considered to use the virtual kubelet to simplify the scheduling, assuming every node could be every cluster could be a virtual node, and even porting your new proposal for the kind, I don't remember the conditional taint to the SCG node, for example, because I think on a node today we can't have a navigation on a taint based on condition. It's hard-coded on the kubelet based on pre-built conditions. But this extension can make sense also on a node. And considering every cluster as a virtual node with a lot of resources, a lot of things, also solve this problem of cache, what you were speaking about, because you have every pre-computed node on your master cluster, and you see them as static nodes.
That's a very good question. So actually, in the early days when we are designing the multi-cluster architecture, virtual node is one of the option. Why we choose the federated way? So basically, considering, managing directly the clusters is because that if you do go through the virtual kubelet way, you are kind of scheduling pods, a pod to a cluster. You still need to kind of resume the workload information when it goes to the member cluster API server, right? If I want to schedule a state set and deployment, or even a custom resource workload definition, the pod API is not that ideal for carrying the extra information.
Yeah, because in fact only the pod will move to the node. But yeah, I see what you mean. So the deployment and stateful state will remain in the master cluster, and only the pod will move.
Yeah, most of the fields are remain the same. Yeah.
Yeah. Okay, yeah, makes sense. Thank you. But the conditional taint still makes sense in node. No.
Node level, right?
Yeah.
Yes.
Okay, thank you.
Yes.